Welcome to our first well test analysis video assignment. We are from group 1 and today we are going to explain to you the interference test. So before we delve into the topic, first let's try to meet the lesson outcomes for today. First, we want to explain to you the basic concept of interference test. This will be done by me, Ashwin Ray. Second, we want to explain to you the mechanisms behind the interference test. This will be done especially by Monchol. And third, we want to apply the interference test in estimating reservoir properties. This will be done later by Mr. Hamizi. Now, let's just go roughly on the concepts of interference test, Firstly, interference test is also known as the communication test. And what you need to know, interference test is a multi-rate test. So what does multi-rate test mean? That means multi-rate test, that means it always involves more than one well. So in our case here, we try to achieve at least one active well and one observation well. Examples of active well would be injection well and also a producing well. And for the observation well, it's definitely usually a shut-in well. Okay guys, now third, how it works in the most simplistic way is by you creating a transient on the active well. Listen, on the active well you do a transient and you check the effect of transient on the observation well. Check the effect of transient. This is what happens. You create a transient in the active well, then you check the effect of transient on the observation well. But this will explain to you in detail by Monchol later. And lastly, as I said just now, we want to check the effect of transient in the observation well, How do we check the effect? By using a pressure gauge at the observation well. Here, the pressure gauge measures the effect of pressure in observation well. So there you go. These are the simple, most simplistic concept of the interference well, also known as the communication test. So now, what is the objective of doing this interference testing, The most fundamental concept of you doing this interference testing is to evaluate the communication between the well. Like I said just now, if there is communication, that means there is if there is communication, that means there will be a pressure response. If there is no communications, that means there will be no pressure response. Now let's just say there is communication that exists, This will actually lead you to provide estimates of the reservoir properties. Examples of reservoir properties that you can get from interference testing is permeability and storage capacity. How do you get these estimates, The estimates of permeability and storage capacity by using a type curve matching. Now this will be explained to you by Hamizi later in detail. And thirdly, we want to investigate the directional properties of permeability. This is also known as anisotropy. Something that you might have heard probably in your second year or something like that. Anisotropy, what this basically means here is that the permeability is different in different directions of the well. So probably the permeability moving the left side of the well is different to the permeability moving to the right side of the well. Here might be 0.2 md, here might be 4 md. So we want to investigate the directional properties of permeability. We can use interference testing here. And last but not least, we want to check if fracture is in communication with adjacent well, because there will be fracture in between two different wells. And now in the latest technology, hydraulic fracture is very high in demand. Everybody is using it in industry. And now what hydraulic fracture is capable of doing is two things. It can knock offline an adjacent well, or it can also intrude the adjacent well. By knocking offline means you won't have communication between wells anymore. No communication. But then if you intrude an adjacent producing well, the bad thing that happens here is you water out the adjacent well. So this is assuming that both wells are producing well, right? If you knock off, there won't be a communication. But if you intrude the adjacent well, producing well, you're watering it out. So initially, probably the adjacent well had a lower water cut, maybe 40 or 50, but because you water it out, you have a higher water cut, which is 80, which becomes not commercially viable anymore. So this is what we want to do to check if the fracture is in communication with adjacent well. Okay, done with the objective of interference testing. Now, there are certain limitations when it comes to interference testing. Firstly, it takes considerably longer time. Why? Because of the distance. Because you have to understand there is a very big distance between these two wells, right? So it might take up to 2 to 3 months just to run this test, and it's a very long time. And during this period, you can do a lot of things instead of just waiting for this test results. And secondly, you require a very sensitive pressure recorder, because the pressure transient that might be observed in the observation well can be as small as 0.01 to 0.05 psi. As you can see, this is a very small pressure. So for this, right, you might need a very accurate pressure recorder, or else you might miss this and you might assume that there is no communication. So example of sensitive pressure recorder would be SPIDR pressure recorder, which is now used a lot in the industry. And thirdly, it takes up a lot of cost just to do this, because as I said just now, it can take up to 2 to 3 months just to do this, to carry out this test. And during this long period of time, probably you can use the well to reproduce, or probably there are some other things, and probably the equipments involved in this are very expensive. So it takes up a lot of cash, and it takes up a lot of time also. And lastly, it's very difficult to maintain the flow rate over an extended period of time. So here you go, the 4 limitations. You know the objective, you know the limitation, and you know the basic concept. Now let's move on to the mechanisms of the test.
Everyone, my name is Munchol. I would like to start from what I seen as a stop. So my part is to discuss more about the mechanism of interference test. So to carry out the interference test, the requirements that we need are the active well and then the shut-in well within the same reservoir. So for this case, active well is sometimes referred to as shut-in well, is mostly referred to as the observation well. So to make you more a bit clear about how this fracture interference test work, so I have a diagram that I will illustrate so that it can make you satisfied with how this mechanism works. In this diagram, you can see we have the entire reservoir, and this entire reservoir has 2 wells which are distant away from each other. So the first well is called active well, as I mentioned before. In this active well, we are producing at the constant rate, that's R. So from there we have the shut-in well, which is R away from the active well. In this well, that's the shut-in well, is where we are going to observe the fracture response. And we can observe the fracture response using the fracture gate. So we record the fracture response in the shut-in well. So the outcome here, when we measure the fracture response in the observation well, we are going to see whether there is a change in the fracture in the shut-in well. If there is a fracture response in the observation well, then we can conclude that there is communication. Sorry, I mentioned the second part. There is a communication between 2 wells. And if there is no any fracture response in the observation well, then we can conclude that there is no communication. There is no what? Communication. Why? It is because there might be a presence of of fall or any barrier between the two wells. So that's why there is no any response in the observation well. So as you can see from the graph, we have pressure here. That's our initial pressure. As you can see, is from 5,000. So, and you can see here, there is a production here, and then it is stopped, and then the pressure start to build up. That's what we call pressure build up. And here we are producing at the constant rate. And then now here in the shading well, this one, the second graph is about the observation well. In this one we see the response. So this is now the response that we talked about before in the shading well. So you see here, there's a communication between the two wells. And if there's no communication, then we can say that there is a fall, as you can see from this last diagram. So they are away from each other. So any pressure change here will not have impact here on the shading well. It's because there's a barrier here between these two wells. So there's no link between the two wells. So how do we detect fall? In case of fall, as you may see in the graph that my friend is going to explain, so the derivative is stabilized at Vd is equal to 1 at late time. And in case of true fall, a pressure and derivative curves are a straight line of the slope half. And that's it. Hope you enjoy.
Hi guys, my name is Muhammad Hamizi. I will explain to you about type curve matching that is used in interference testing. Before that, let me remind you that we use type curve matching to determine permeability and porosity. Now, let's say we got two wells. The distance between these two wells is R. The effect of producing well at this observation well is given by a line source solution. The solution is delta P However, this line source solution is only valid when Kt over porosity mu Ct R squared is greater than 25. Due to fact that R is very large, thus Kt will be smaller than 25 because the R is very large. So we get the result is smaller than 25. It means that we need to run the test for such a long period of time. It is not economical. So semi-log analysis is not possible. So a more convenient way to analyze such tests is using type curve analysis. To use type curve analysis, we need to solve the equation in dimensionless form. Here is the equation in dimensionless form. It is PD equal to half ER d squared. PD stand for ER, RD stand for R over RW, and TD stand for
Kt over porosity mu Ct RW squared.
So here is the difference between the two equations. We change this equation into dimensionless form and we get this as the result. Okay, now let's move to the type curve matching. I will show you how to match these two graphs using the tracing paper. So the first step is plot log PD versus log TD over RD squared on a tracing paper. Then we locate the line source solution, which is this line. The third step is we put this plot on the log delta P versus delta T. This graph is called the master curve, and it is provided. So we put this graph on this master curve. The next step is we match the field curve and the type curve. This one we call it field curve, type curve, and this one we call it field curve. Then we match these two curve and pick a match point, which denoted by M, PDM, delta PM. And when we get all these match point, we can proceed to calculate permeability, porosity, and storage capacity. For permeability, we use this formula PDM.
Our delta PM equal to 2 pi CH Q mu B.
These two value can be found by the matching of these two curves, and by arranging this equation we can find K. The same goes with porosity and storage capacity. Rearranging this equation we can find the porosity and storage capacity. I think that's all from me. Thank you.